Okay, now we'll start with our first lecture by Frank Verstraete, who will tell us about entanglement.
Okay, so thank you very much. It's a great honor to be able to be a speaker here in this beautiful lecture hall. So I will talk about entanglement and phases of matter. This was the title. I didn't choose this title myself. I think it was probably Ignacio who said that I proposed this title, but it turns out to be exactly the kind of things that I have been interested in for the last 20 years, and I would like to convey a little bit so not just the historical, but actually also like why are we interested in why is there actually some natural connection between phase of matter and entanglement. So it turns out that entanglement gives you a new language, or entanglement theory gives you a new language for tackling the quantum many-body problem. And if you're not a physicist, you might not realize that actually the last 100 years in quantum physics has effectively been like just a consequence, or like a whole sequence of kind of ways of trying to solve the quantum many-body problem. So the quantum many-body problem is the central problem in quantum physics. It doesn't matter whether you do quantum chemistry, whether you do condensed matter physics, statistical physics, high-energy physics. It's everybody kind of struggles with correlations, with the fact that if you kind of have a many-body problem, the Hilbert space is growing very quickly, and you have to kind of, in one or the other way, be able to deal with it. And entanglement theory gives you a new language for tackling this. And once you have a new language, of course, you also want to develop the vocabulary, but especially the semantics. And you want to understand what does it give me of new insights into the structure of the quantum many-body wave functions that effectively govern the world. So let me kind of set up before I kind of give you the overview of what I will talk about. So we want to understand ground state wave functions of quantum lattice systems. Okay, this could be spin system, fermions, on a lattice. It doesn't matter whether it's one dimension or higher dimensions. So all of these things will be allowed, but it doesn't have to be a ring. It can be open, but somehow you have tensor product structure. That's the important thing. It's a many-body problem on a Hilbert space with a dimension that grows exponentially in the size of somehow in the number of spins that you have. And of course, the typical example of such a spin Hamiltonian is something like the Heisenberg model. So it's basically some Hamiltonian. So it's a Hamiltonian that acts on neighboring spins, all the neighboring spins on your lattice. And these are the Pauli matrices. And you're interested in the ground state, especially the ground state of these systems, because indeed this turns out that for many kind of real systems in condensed matter physics, but also kind of in quantum field theory, the ground state is the one that is the most interesting state. That's the one that you want to understand, because all the rest, like particles and all these, are just some small fluctuations on top of the ground state. So we will be kind of interested in understanding ground states of such many-body systems. And indeed, so these spin systems are a bit ubiquitous. Okay, so I think the first person to really kind of study these quantum spin systems was Heisenberg, because he wanted to understand magnetism. So you can study quantum magnets, but actually now can also perfectly model cold atoms. This is for example, a very famous paper of Ignacio and Peter Zoller, where they indeed kind of use these spin systems, the Hubbard model, the Bose-Hubbard model, to model really kind of experiments or to see kind of experiments with cold atoms. You have lattice discretizations of quantum field theories. There's many kind of cases where these things come up. And what is interesting in these systems, and that's the reason that people kind of are so excited about this, is that they show many of the features of the real kind of thing. So typically these Hamiltonians are toy models, but they really kind of give a very kind of simple kind of the physics somehow of these models, or the phase transitions that these models will kind of be able to kind of go through if you vary the parameters in these Hamiltonians, mimic really well what is going on in nature. So to understand the many-body problem, it's kind of this is one of the crucial things to deal with. So let me kind of tell what I will try to convey in this talk. So very brief introduction to the theory of entanglement, only kind of the very kind of things that are relevant for the rest of the talk. I will talk about the phases of matter, matrix product states, again, phases of matter, generalized symmetries, dualities, higher dimensional things, and if there's time, I will also kind of try to make the connection to quantum error correction. But I think many of these topics will also be kind of covered by other people in the next talks. So I have to apologize if I'm not I will go quickly through some of these things, but I'm sure that many of these things will also be covered in a much more detailed and better way in the next talks. Okay, so So what is entanglement about? Okay, so when you have this quantum spin system, you have like a wave function, and so we'll be considered with wave functions. This is already very different to what people do in many other fields. Like in high energy physics, you typically don't work with wave functions. You work with partition functions, or you work with path integrals. But we will be concerned with wave functions. We want to understand the ground state of the wave function. Why is this? It's because actually for the cases where you have interacting systems, this is a very natural representation. It turns out that somehow for interacting systems, it turns out to be very hard to kind of just do the perturbation theory on top of some free fermion systems, and you want to kind of do these things in a different way. But there's many reasons why we're interested in the wave function, but this is the central topic. And so when you have a wave function of many particles, you have a tensor product structure. No? So you have spin 1, spin 2, spin 3, and so further. And whenever you have a tensor product structure, there will, of course, be the possibility there's correlations between somehow the different parts of your tensor product structure. And the theory of entanglement is exactly somehow a resource theory which quantifies which quantum states can be converted into each other by local operations and classical communication. So let me be a little bit more precise. You kind of divide your big system into two pieces. This would be like A, typically called Alice. This is B, Bob. And then you're interested, what can I convert, or what kind of states can I reach by just doing operations on this system, by doing local operations. So these are, in quantum information slang, these are called kind of CP maps. And then depending on the operations you do, you send classical information to Bob. Bob does something. Then Bob does an operation, kind of maybe a measurement, a generalized measurement. Depending on the outcome, he again sends this to A and so further. This is this so-called class of local operations and classical communication. And people want to know, like, under these operations, what can I do with these states? And or if I give you two states or two entangled states, is there somehow a way of connecting them by such LOCC operations? Actually, this, I don't, as far as I understand, this class of LOCC, except this operational way, has still not been completely characterized. So it's still a mathematical open problem to completely kind of understand what this class is. But this is, of course, a very operational way of looking at entanglement. Entanglement is basically a resource theory. It will allow me to maybe violate Bell inequalities, to do cryptography, things like that. And you're interested, how can I change a state that is entangled, but I cannot kind of do operations among, cannot do quantum operations that connect A and B. I cannot kind of create entanglement. I can only do local operations and send classical information. Okay, so let's kind of divide your system into two pieces. This is basically your system from Alice. This is the system from Bob. You have your tensor product. Turns out that every state can be written down in some canonical way. From the point of view of linear algebra, this is equivalent to the singular value decomposition. Okay, you have like you can do any unitary transformation, and depending on a basis, or quantum mechanics, of course, you can choose the bases in which you work, and there's always a basis for writing any bipartite system such that of this form. You have an orthogonal basis in Alice's side, an orthogonal basis in Bob's side, and somehow these vectors are always the same on both sides. And there's a prefactor, the square root of lambda A, and this lambda A will turn out, this is called the Schmidt spectrum, or these are also the eigenvalues of your reduced density matrices. So I'm just repeating things that probably everybody already knows, but nevertheless, let me quickly go to the thing to kind of clarify what is the importance of this entanglement spectrum. So there's a very famous theorem of Nielsen, and it has kind of been refined by many other people, that effectively tells you that I can, under LOCC operations, map a state psi to chi deterministically under such operations if and only if these Schmidt coefficients, or somehow these eigenvalues lambda A, are majorized by somehow the ones of B. So what is this kind of majorization called? It means that actually if I write down all these Schmidt coefficients in decreasing order, that the largest one of this, the one of psi, is smaller than the largest one of chi, and so further. So this is smaller. So basically, if this lambda is smaller than mu, like if these Schmidt coefficients are kind of majorized by this is a very famous concept, of course, also in classical statistics, then it means that actually this lambda is more random. It's more kind of stochastic. And indeed, this is one of these kind of very well-known properties of entanglement, is that somehow the more entangled you are, the more locally, the more stochastic you are, the more random you are. And that's exactly somehow the manifestation of this. Okay, and this is an if and only if. And indeed, if the largest eigenvalue of reduced density matrix is small, that means that you must have a lot of entanglement. Okay, because if the largest is small, that means that there's other ones that also kind of, there's many more that have to come. And the more eigenvalues you have, the more entanglement. And okay, so this is basically for one copy, and then you can start saying, okay, but what happens now if I have access to many copies? Okay, if I kind of not just have one state, but I have many states, I can kind of take the tensor product of many of these copies. Of course, there's still only one Alice and one Bob, and the question is, how many states of psi can I convert in the state of chi? Now, there's some kind of these Schmidt coefficients. If you take many kind of powers, then an argument very similar to Shannon's argument means that actually the only property that you need to know that if I take many Cardiff copies, so I take the power of all these kind of things, the only thing that matters to know whether lambda is majorized by mu is just to calculate the entropy of somehow this distribution. And so you will be able to convert n times the somehow entanglement entropy of somehow your state psi copies in n times the entanglement entropy of somehow mu. And this is the constant. This is somehow the preserved quantity, and this is this entanglement entropy. So this is like a notion that there's something conserved. I can kind of convert psi to chi and vice versa if and only if this kind of thing is satisfied. So basically, I can convert n copies of psi into m, which is equal to n times s of lambda divided by s of mu copies of chi and vice versa. And this is the reason that people in quantum information theory typically talk about entanglement entropy, because this is the only measure somehow that you need to know to kind of solve this problem. Of course, if you only have one copy, then it's much more kind of subtle. You have to kind of look at these eigenvalues. But if you have many copies and the limit of somehow n and m going to infinity, that's the only thing that you need. And indeed, so it always worried me a bit that people in the field of condensed matter, but also quantum gravity, they only kind of care about this entropic quantity, while actually this does not really have an operational meaning. It doesn't really make sense to say, oh, I have infinitely many copies of my spin chain. Okay, so you actually have only one copy of your spin chain, and therefore this is actually the more natural way of looking at entanglement. Okay, so let's look at an example. So I talked about this Heisenberg spin chain in the very beginning. So basically, you can take all this spin chain. Okay, like let's take a one-dimensional line of spins. So the dimension of this Hilbert space in the case of a spin-1 Heisenberg chain is 3 to the n, with n the number of sides. You can divide your system in two. You can say everything to the left here is Alice, everything to the right is Bob. Okay, let me look at the ground state of that system and look indeed at these eigenvalues. Actually, so Lee and Haldane in a very famous paper of 2008, motivated by actually by quantum Hall states, but indeed somehow here we kind of limit ourselves to a much simpler example, namely to the spin chain. Actually, it turns out to be very useful to take the logarithms of these Schmidt coefficients or of these eigenvalues of the reduced density matrix, because then this has the meaning of some Hamiltonian. Okay, because every reduced density matrix can be written down as e to the minus h. Okay, and these are then the eigenvalues of that Hamiltonian. And if you do this for this spin-1 Heisenberg model for the ground state, you see that actually these are, of course, the logarithm. So the smallest one, these correspond to the largest eigenvalues. There's twofold degenerate, and you get 4, you get 2, 4, 4, and so forth. So these are the Schmidt coefficients. So they come in a very kind of nice kind of sequence, and they seem to have some symmetry properties. And this will be one of the key things that we want to understand. We want to understand where is this coming from, or what is this a signature of that indeed you have these Schmidt coefficients. So this is a logarithmic scale, so that means that actually if you look at these Schmidt coefficients, they decay very, very quickly. Okay, so there's actually not that much entanglement in a ground state of a quantum spin system, and this will actually be the key in understanding ground states. And this is actually the reason that we will be able indeed also to solve for these problems and actually come up with an interesting kind of new numerical computational methods to deal with somehow this problem of simulating ground states of these strongly correlated systems. So, and this is called the area law. The fact that this decays very quickly, these Schmidt coefficients, actually has to do with the fact that you have something like an area law. An area law in one dimension is trivial. It means that actually if you calculate the entanglement entropy as a function of the size of this block, of this yellow block, then of course in one dimension it does not depend on the size. Okay, so at some point you kind of saturate, and indeed this is why we can even plot these Schmidt coefficients. If you kind of go to a two-dimensional system, then this area law would mean that actually the entanglement entropy scales like somehow the linear size of the boundary of your kind of system, and that's why somehow, of course, the area, as people call it an area law, because they have in mind that you have a three-dimensional system, and then somehow you just have a two-dimensional boundary that you're kind of interested in. But this is the first lesson. Actually, if you look at an actual system, an actual spin chain, and look at the ground state, there's very few entanglements. Okay, so there's another kind of idea of entanglement that I really wanted to talk about, because it certainly guided everybody that's working in this field very much towards kind of trying to understand indeed the role of entanglement in many body systems, and something that's called the monogamy of entanglement. Okay, so entanglement has a property that the more I'm entangled with somebody, the less I can be entangled with somebody else. That's why, of course, this is called the monogamy property. And actually, you can really write down very precise statements there. Okay, so for example, if you have a system B that itself consists out of many parts, then the entanglement somehow of row A, B, so somehow if you look at the reduced density matrix of A with the whole of B, is actually larger than the sum of these things. So I did not really define entanglement for mixed states because that's what you have to do here, but it's just, okay, I just want to give you the gist of the discussion. So somehow you have some entanglement measures for density matrices. These are the mixed version of these pure states, and somehow these have to be true. So, but if you kind of, in particular, if you would have like a subsystem A, okay, and then a subsystem B that consists of many parts, but there's some symmetry of these many parts. So think about a lattice system, okay, and A would be the central spin, and B would be all the spins next to it. So this would be B1, B2, B3, and B4. Okay, so this is basically a lattice system. I'm interested in the ground state of that system. Because of symmetries, if somehow let's assume that the ground state of that system is unique, then it will actually indeed kind of be completely symmetric. It will have all the symmetries of your lattice, and that means that this row A B1 will be equal to row A B2, be equal to row A B3, and row A B4. So all these reduced density matrices will be equal. You plug this in this monogamy inequality, and you see that indeed the entanglement between these two is actually bounded to something divided by the amount of neighbors that you have. Okay, and this already clarifies that if you go to like a 2- or 3-dimensional system, there can only be very few entanglement in your system. Okay? Because if you have to share the entanglement with your neighbors, you cannot have very much of it. And actually, this is somehow you can turn this into rigorous proofs, and actually this allows you to define indeed that in infinite dimensional lattices, actually mean field theory is exact. You don't need entanglement at all to kind of work in to find ground states in infinite dimensional lattices. And indeed, if you are interested in ground states of many body systems, it turns out that the lower the dimension, the more important entanglement becomes. Okay, and that's actually one of the main reasons that indeed the physics of 1D quantum spin chains is actually so interesting. And actually also of 2D quantum spin chains, there's entanglement plays a very important role, and this can be traced back somehow to this property of the monogamy of entanglement. Okay, so let's change gears now and try to understand how entanglement is created. Okay, so let's, I think everybody has at least had some introduction in the field of quantum computing. So you basically have some quantum bits, some qubits, and you have some gates that act on it. So let's say nearest neighbor gates, and you have time that acts on it, and you're interested, okay, how much entanglement can I create? And actually this will be a key in understanding phases of matter. Somehow this whole idea of how much entanglement can I create in a certain amount of time will be a key in identifying somehow the entanglement properties of many body systems. So you kind of have time, and you kind of go down and you ask, okay, how much entanglement can any one of these bits create if I divide my system into 2 pieces? This would be A, this would be B. Turns out that any one of these gates, if they're acting on qubits, can create at most 2 E-bits. Okay, this is a bit surprising, actually, that it's 2 E-bits and not 1. The reason is that if you kind of take, indeed, 2 maximally entangled states, so this would be A1 and A2, B1 and B2, so this is a maximally entangled state of 2 qubits. If I swap these two, this is a 2-qubit gate, I will certainly have 2 E-bits. I will have, this one will be maximally entangled with this one, and this one with that one. Okay, so this is why it's a bit subtle. So if you kind of apply quantum gates to systems that are already entangled, you can certainly kind of do much more entanglement. Okay, but this is, anyway, but this is still the maximum. You can only do 2 E-bits, and this actually has to do with the fact that, say, the Schmidt numbers of this quantum gate, there's only 4 different Schmidt numbers, and you can actually mathematically easy kind of come out, understand why this is true. But anyway, so the important thing is that a constant depth quantum circuit can only create a constant amount of entanglement. Okay, so this is, of course, so for people in quantum information, they know this. We are not interested in constant depth quantum circuits typically because somehow they are, well, I can actually simulate such things using NPS. We will kind of introduce this later, but exactly because there's nothing really kind of complicated to them. So of course, I'm also assuming here that maybe the quantum circuits, that the gates are acting only on nearest neighbor and so further, because there's some notion of locality that is important in these things. But anyway, so this is obviously the reason why quantum computers must exhibit large circuit depths to be useful. Otherwise, you will be able to simulate this. And actually, this simulating quantum many body systems was one of the main reasons actually that people started thinking indeed about these tensor networks that I will kind of introduce, because you wanted to make this. With this, you can indeed kind of see this very easily. Okay, so this is the last kind of slide I think I need about entanglement theory, but this was a very kind of, there was a long-standing open problem that is actually the key in understanding from the mathematical point of view, what a phase of matter is. Okay, so that indeed somehow a phase of matter, somehow you will see that indeed in a given phase of matter, somehow all the states will effectively have the same amount of entanglement. And to prove this, you need something like the continuous version of somehow this statement here of how much entanglement can I create with some case. So assume that you have a big system. Okay, so you have A consists of a small a and a big A, small b and big B. I have a Hamiltonian term acting on big A and big B, and I'm asking how much entanglement can I create as a function of time. So what is the rate of entanglement that can be created by evolving somehow this system with a Hamiltonian that only acts on big A and big B? And you see, this is not trivial, because we saw that if this thing is entangled with something else and this is entangled with something else, suddenly you have much more power instead of one e-bit, because of course, if you just have writing on two, one e-bit, wherein you could create two e-bits. Not obvious at all happens in the general case. And it turns out that this case still proves that this entanglement rate is actually bound by the log, basically the norm of this Hamiltonian term, but also the log of the minimum dimension of this big A and big B. So it's not dependent on somehow this small a and this small b. It's only depending, and very importantly, logarithmically on big A and big B. Okay, so this turned out to be kind of the key in understanding the entanglement properties, that if you're kind of in a certain phase of matter, the way we will define what the phase of matter is will implicitly use somehow this fact that this makes sense. Okay, but you'll see, I will kind of try to convey this. Okay, so let's indeed kind of move to this question about phases of matter. Okay, so phase of matter. So I recently wrote a popularizing book in Belgium and Dutch actually about physics, and I was kind of saying, well, one of the deepest insights in physics of the 20th century was basically this whole Landau paradigm, that symmetry is the central kind of idea to understand physics and many body physics, and that symmetries especially become interesting when they break. Okay, and this is of course, I think, why Landau always had this asymmetrical hairdress, because this must have been on purpose. But anyway, I got a very angry email from a reader who said that Pierre Curie had already said exactly the same thing, and that he realized that for many body systems that this is the key in understanding somehow their properties. So I think this is, well, I got this out of an English text, so I'm not so sure that there's a literary translation of what he said, but nevertheless, it's very, very interesting. So he basically says that symmetries, well, you have a certain system with characteristic symmetries, but then you say, okay, systems can break the symmetry, and indeed, that what is necessary that certain elements of the symmetry do not exist. This symmetry is what creates the phenomenon. So this is exactly, of course, the whole point, that matter becomes much more interesting if a symmetry is broken. And indeed, this is basically the Landau paradigm. If you kind of have one of these many body systems, so you have this set of Hamiltonians defined on a spin system, with a certain symmetry. Okay, so this is so phase diagrams or phase of matter only make sense if you kind of impose some symmetry to your whole system, because otherwise somehow the whole thing does not really kind of make sense. At least in there's a situation where it still makes sense, but nevertheless, in the typical case for the Landau paradigm, you have to say, look, I have a certain system with symmetries, and I will kind of be much more precise later what that means, these symmetries. And I would like to characterize a phase diagram. If I vary the parameters of my Hamiltonian, you want to see how the ground state wave functions change. What are their properties? How do they depend on the parameters that I can change? And what you will see is that you get different phases of matter. And all these different phases of matter are actually related or kind of labeled by somehow the subgroups of the characteristic group that are still there, and therefore also by the other symmetries that are actually broken. Okay, so this is indeed this whole Landau paradigm. And of course, Landau then worked out this whole idea of local order parameters that characterize these different phases. That somehow, if you have a magnet, okay, then in the magnetic phase you have an order parameter, namely the magnetization, and in the disordered phase, in the paramagnetic phase, there is no order parameter. At least to the first sight, there's no order parameter. We'll kind of come back to this later. But let's indeed be a little bit precise, because I actually will use this example later in the talk. So this is just a spin-1 Heisenberg model with an A4 symmetry. Okay, so this is effectively, what does that mean? So I have a Hamiltonian that consists of a ring or a spin chain. In this particular case, it's actually a spin chain with open boundary conditions. And this spin chain has like nearest neighbor interactions that are of this form. So I have a spin-1 Heisenberg model. So my degrees of freedom on every side are 3-level systems. Somehow this consists of somehow a Heisenberg term, something like this Heisenberg term squared, and then some other kind of term that you can derive. And you can see that indeed all these different terms, all these HI alphas, they commute with the tensor product of local symmetries that form somehow a representation of your symmetry A4. So A4 is, of course, just the alternating group with 4 elements. Okay, so this is this is just a group, and if you act with somehow the symmetry on every one of the spins together, so that's why it's called a global symmetry, you commute this. Okay, so this is the symmetry that Landau talks about. You have to start with a Hamiltonian with terms that all have a certain symmetry, and then he says that actually the phase diagram, if you kind of start varying these parameters J1 and J2, and you plot what is somehow the characteristic phase that I will get, you will get a phase diagram that looks like this. Okay, this is of course a very rough sketch, but somehow this will be important later for the talk. And what you see is that actually there's different phases. There's phases where your A4 symmetry is not broken at all. Okay, this is the A4 symmetric phase, so there's no symmetry breaking. So here you have completely symmetry breaking. Here you break a subsymmetry, and then actually it turns out to be that there's also a very interesting phase that actually does not really fit this Landau paradigm, and this is called a symmetry protected topologial phase. Okay, this is of course when somehow this J1 and J2 are 0, this turns out to be the Heisenberg model, and the Heisenberg model is known to be somehow in an SPT phase. This is in the so-called AKLT phase, the Haldane phase. And I think this is one of somehow the things that we want to understand. We want to understand what are these different phases? How is the entanglement in these different phases distinguished? How can I kind of understand if I kind of have a ground state of a system and I look maybe at its Schmidt coefficient or its entanglement degrees of freedom, that's where we will go to. We will immediately be able to say in what phase this state is lying. And therefore, I will be able to understand that indeed the entanglement structure of all these different ground states in these different phases is completely different. But in a certain phase, the entanglement structure is very much the same. And then certainly, if I go from one phase to another one, I have a phase transition, and that could be a first or a second order phase transition. Okay, so let's now try to define what a phase of matter is. Okay, so this is basically, you see that if you simulate this and you vary your parameters a little bit, you kind of change your properties a little bit. How can you make this hard, or what is the mathematical way of defining at the end what a phase of matter is? So we'll say that two gapped Hamiltonians with the same symmetry G, because it was important to have a symmetry, because otherwise you cannot even label these things. So that actually also means that if you break the symmetry, then many of these phases can be connected. Okay, so it's only when all the terms in a Hamiltonian have the symmetry, there's no way. But anyway, so I have two gapped Hamiltonians with the same symmetry G or in the same phase. If there is a symmetry preserving adiabatic path interpolating between them without closing the gap, even when the size of the systems becomes infinitely large. Okay, so this is basically a modern way of defining what a gapped phase of matter is. Okay, so I have a symmetry, and now I have a certain kind of class of states that can all be connected into each other, can all be transformed into each other by kind of changing the parameters of my Hamiltonian a little bit. And you can see that actually the gap of this Hamiltonian, which is actually the difference in the energy between the ground state and the first excited state, if that gap does not go to 0, even in the limit when the system goes to infinity, then I have then this path is gapped, and I say that these two states are in the same phase. So colloquially, from the point of view of quantum information, you say, okay, there's basically a low-depth quantum circuit where all the gates have indeed a symmetry, commute with this global symmetry that map the ground state into each other. There's a low-depth quantum circuit that maps them into each other. Okay, so how do you prove this? This is a paper that I'm very, very fond of, that I wrote with Sergei Brovey and especially with Matthew Hastings. Matthew Hastings is really the hero in this whole, in this story. He was, I think, the first one to really kind of realize that entanglement theory is, together with Saigon Wen, but Hastings is really the one who proved it, that entanglement theory is the key in being able to come up with such definitions of what phases is, and that they also kind of make sense. Okay, so Matthew Hastings, what he did is actually introduce something that's called Lieb-Robinson bounds. And the Lieb-Robinson bound is effectively telling that even if you have a Hamiltonian, and because this is just normal non-relativistic quantum mechanics that we are doing, that even if you there's no light cone in such systems, in principle, you could be able to signal arbitrarily fast, that the amount of information or time that you need to send information from one part to another part grows somehow. There's some kind of on a finite speed at which information can travel, and this is this so-called Lieb-Robinson bound. And somehow the information that leaks out of that kind of cone, this information cone, is exponentially suppressed. So what is this very ingenious kind of construction that he then came up with? This is something that he called quasi-adiabatic evolution. He says that if indeed I have a path of Hamiltonians have different Hamiltonians in this phase diagram, and I want to kind of understand whether I can go from one to the other one, there's actually an exact Hamiltonian that I can write down, and if I evolve with that exact Hamiltonian, but there's a Hamiltonian, a different Hamiltonian that's a bit more non-local. Okay, so you start with a given path of Hamiltonians, and you dress this Hamiltonian a little bit with other terms, but terms that are exponentially decaying in the distance, so it's still an almost local Hamiltonian. If you evolve with this almost local Hamiltonian, you will kind of map every ground state in that phase exactly into each other. Okay, so he was able to see that indeed this definition that I just gave makes sense, that if you have a state and you kind of evolve it with this dressed Hamiltonian that is still quasi-local, somehow you will be able to kind of map one state, one ground state, exactly to any other one in the same phase. Okay, so if you connect this now with this small incremental entanglement theorem, this entanglement theorem that I talked to you about, that tells you how much entanglement can you create as a function of time with a certain Hamiltonian. Okay, there was this logarithmic dependence on somehow the Hilbert space dimension. So basically immediately implies this theorem that all states in a given phase have the same entanglement entropy, up to a term which scales linearly with the boundary of the region. Okay, because indeed, somehow this evolution with this quasi-adiabatic Hamiltonian that is kind of local but has exponentially decaying terms can only create an amount of entanglement that is kind of scaling like the boundary of the region on which somehow of the whole system. So if I'm interested in the entanglement entropy of A versus its complement, somehow putting this quasi-adiabatic theorem together with this entanglement rate kind of ideas can see that indeed somehow the entanglement in all these states in the same phase somehow must be related to each other by just a boundary term. And more specifically, if one state in a phase satisfies an area law, then all of them do it. Okay, so that means that's something very special, that even if you find in a certain phase one state that has very low entanglement, then actually all states in that whole phase will have very low entanglement. Okay, and that's, of course, that's the start. That's a very interesting kind of prospect. It means that indeed we should be able to use this, to take advantage of this, to come up with new methods for actually simulating ground states. And indeed, but before do this, let's define somehow the set of short-range entangled states. Short-range entangled states are actually all states that can be created using adiabatic paths interpolating to a product state. So basically the low-depth quantum circuits acting on product states. Okay, so these are basically all the states, well, the states that I can create. I have a product state, and this is, for example, the ground state of a trivial Hamiltonian that only would have a magnetic field, and then you start perturbing this, all the states, as long as you don't reach a phase transition where the gap closes, all the states will satisfy an area law. And indeed, for gapped spin chains in 1 + 1 dimension, so this is just a one-dimensional quantum spin chain, so I have a ring or an infinitely large spin chain, it does not really matter. It turns out that every state is a short-range entangled state, and therefore they all satisfy an area law for the entanglement entropy. And this is this famous theorem of Matthew Hastings that indeed ground states of gapped spin systems all satisfy an area law. Okay, and this is somehow the idea is that indeed there's only one phase. So there's only one phase as long as you don't impose any symmetries. Okay, so as long as the adiabatic paths that you allow for don't have constraints, symmetry constraints, I can connect everything to everything. There's only one phase in 1D. Okay, so that means that, but to get something interesting, of course, I will have to do something. I will have to break this. I will have to impose it. And indeed, I could impose some symmetries, for example, a Z2 symmetry. And then somehow, suddenly, it could be that you have phase transition. And this is exactly what will happen. Okay, that's exactly why these phases of matter will be parameterized somehow by the subgroups and somehow groups and subgroups that I can break. So once you impose that all the gates or the Hamiltonian terms in your system have a certain symmetry, there's no kind of guarantee anymore that I can connect them to a product state without going through a phase transition. Okay, because I have some constraints, and indeed, this is particularly relevant, of course, if the symmetry would become a super selection rule, and that's exactly what happens if you have fermions. If you have a system of fermions, like a spin chain of fermions, so-called Kitaev chain or the Majorana chain, actually this Z2 symmetry is not just a symmetry, it's actually a super selection rule. You cannot break it, and indeed, this is the reason somehow that this is a truly topological phase. There's no way in which somehow you will adiabatically be able to connect the ground state of this Majorana chain to the one of a trivial kind of case, because somehow the Hamiltonian paths that would do that, they would break the Z2 symmetry, and this is not allowed for a system with super selection rules. Anyway, higher dimensions, this whole story is much more interesting, actually, because exist genuine non-short-range entangled states. These are the so-called topological states. These are the states that have topological order. For this, you don't even need to impose symmetries. And these are exactly the ones that are of interest to, it turns out, to people in quantum information theory or somehow in the context of quantum error correction. These will be somehow the states that are relevant or very much related to building quantum memories. But anyway, so what is still probably true is that every phase, even in higher dimensions, somehow has one fiducial state satisfying an area law. So for example, all these quantum double states or string net states that are very popular in the condensed matter theory community, but also somehow in the quantum information community, these turn out to be, well, these very specific states turn out to be states that actually satisfy an area law, and that means that the whole phase, all states that are in that phase by perturbing them, will also satisfy an area law. Okay, so there's very few entanglement in all these systems. So this is how the whole point. And this leads to the question, can we kind of create now a variational class of wave functions that parameterize all states satisfying an area law? Okay, of course, this will depend on the dimension. In 1 dimension or 2 dimensions or 3 dimensions, we'll have a completely different setting. And again, so also we are only kind of, for this talk at least, we are only concerned with these lattice systems. No? So of course, it's not enough to have a variational class of wave functions. You also want to be able to calculate observables efficiently. It's not enough to write down a set of wave functions and say, look, this is these states represent very well somehow the ground state of my system. You still have to be able to calculate efficiently with them. And it turns out that for the case of 1D quantum lattice systems, and maybe even for higher dimensions, the jury is still out. Actually, this is indeed solved. Okay, so this is exactly what happened. These are exactly these tensor network states, these matrix product states. In higher dimensions, they are called projected entangled pair states. So these are the states that somehow in every one of these phases, I actually have one of those. And if I perturb them, they somehow just change a little bit, but somehow their essential features remain invariant. The entanglement features remain invariant, and therefore you can still simulate this using these. Okay, so let me kind of go to the third part, matrix product states. So what are these matrix product states? Okay, so how can I indeed get some feeling of wave functions that are, let's say, ground states of translation invariant spin chains? Okay, so actually, if you start playing this game and start writing, like trying to write down translation invariant wave functions, is not easy. Okay, so if you kind of have a system of, say, a ring of L spins, and you want to understand, okay, what are all the wave functions that I can write down that are translation invariants and have actually a few entanglement? It's a very difficult exercise. Okay, so there's no kind of direct way in which you can do this, and typically somehow all these states that are relevant, if you could write them down in some kind of a particular basis, you would need exponentially many terms in this thing. Okay, but there's another thing. This is called this matrix product states. I will kind of say later who kind of discovered this, but it's a very ingenious construction, and it's actually based on some work I think that was done here in Princeton by collaborators of Elliott Leap. So what they say is that, okay, let's assume that somehow I can break my translation symmetries up to somehow 2 sides. Then it's very easy to write down a translation invariant state. I just take somehow a state with lots of entanglement between particle 1 and 2. So this is particle 1, 2. They are maximally entangled in a high level that is chi. And I just take a tensor product of this. I just put them next to each other. Okay, so this is obviously translation invariant if I shift everything with 2 things. But I want to have a method now of creating a ground state that is actually completely translation invariant. Okay, so how do you do this? Actually, you say, well, let me kind of interpret these 2 particles here, these 2 chi level systems, as being maybe some quarks in some lower dimensional object. So let me kind of write down somehow a projector on that subspace spanned by these 2 high dimensional systems to somehow a D-level system. And I say, actually, my physics is going on in a very low dimensional space in this Hilbert space, this chi-square dimensional Hilbert space. Okay, so that, and somehow this Hilbert space, this projection to a lower dimensional Hilbert space, you can easily kind of parameterize by matrices, by somehow D matrices that act somehow on your chi-squared degrees of freedom. Okay, so because you have chi-squared degrees of freedom, somehow you just tell how these somehow projectors live. And anyway, so you kind of do this systematically, and what you end up with is a way of parameterizing translation invariant states in a systematic way, such that the wave function itself is written as a trace of products of matrices. Okay, so this is like, this would be spin 1, I1, I2, I3, and somehow the amplitude of your wave function corresponding to somehow this configuration would be given by the trace of the products of these matrices, and these matrices themselves are chi-dimensional objects. Okay, so what this way of doing has somehow, so why does this make sense? It means, well, of course, you still have the symmetries of your system, but also somehow you have very strong correlations between nearest neighbor, and the correlations between further neighbors is basically effectively exponentially suppressed, because if you want to kind of calculate correlations between this one and this one, it has to be mediated by this one. And this is exactly what mimics this idea that the ground state of a local quantum Hamiltonian should have extremal correlation, very strong correlations between nearest neighbor, and the correlations that are further away are actually not important for the energy considerations. Okay, so of course there's much to say about this, and I think David will actually give a talk that will be much more focused on this, so that's why I don't spend too much time on this, but somehow this whole idea has led to somehow a completely new way of building, systematically building kind of interesting wave functions. Okay, so you see this whole thing, this matrix product state was built from starting from entangled pairs, and that you start building and putting all these entangled pairs to each other, and somehow instead of matrices you can put tensors, you can also put them in a different geometry, and actually this whole thing has led to kind of seeing this entanglement as a building block, as a Lego block by which you can actually start writing down arbitrary wave functions. Okay, so I should really mention these people. I think they were all in Princeton at some point, Affleck, Kennedy, Leap, and Tazaki. So they are the ones who found a ground state that is specifically of this kind of part. This is the so-called AKLT state that is exactly of that kind that I was writing down. And Vonnes, Nachtergaal, and Werner are mathematical physicists who kind of took this idea and generalized it to effectively the matrix product states as they are. And then Kenneth Wilson and Steve White actually were the first ones to really make use of that and to realize that these states, it's not just a very interesting theoretical construction, but actually very useful to kind of simulate quantum spin systems with. And then this is, of course, Ignacio and Giffrey somehow, and then there's a whole bunch of other people that took this up and really kind of started interpreting the physics and understanding the physics of why somehow this is a good idea. Okay, so this matrix product states, they form a manifold. Okay, so there's actually a very nice manifold. It turns out to be a Kähler manifold, but okay, this is not important for the talk here. But it turns out that using somehow these ideas of Hastings and many other kind of contributions, you can basically understand that all ground states of local gapped Hamiltonians in 1 + 1D can faithfully be represented as a matrix product state. Okay, so that indeed these matrix product states, this manifold of matrix product states, they are actually the ground states of local gapped Hamiltonians in 1D. If you're a ground state of a local gapped Hamiltonian, you will be very close to something that lies on this manifold. And if you actually are a state on this manifold, you are actually a ground state of a local Hamiltonian. And of course, this led to a huge simplification for the study of gapped phases of matter, because instead of working with Hamiltonians, we can directly probe the manifold of matrix product states. Okay, and actually, this manifold is very interesting. Okay? It's a Kähler manifold, but you can start kind of trying to say, okay, let me then, because this just gives me all the physics, let me project actually my full Hamiltonian on that manifold, and you will be able to see that you can do time evolution, you can start kind of using this time-dependent variation principle, you can start understanding many kind of the geometry, like topological indices, all these kind of things are present there. Okay, so, but let me kind of briefly say something about the density matrix normalization group, which is effectively a variational method over the set of matrix product states. So you're guaranteed, if you have a quantum spin chain, that the ground and it's a gap, that the ground state is somehow effectively of that form. So what Stephen White did is effectively destroy somehow this exponential complexity, this wall, this exponential complexity wall for simulating ground state of quantum spin chains. So this was actually an amazing accomplishment. Before that, people had no idea how to simulate many body systems, spin chains, because actually, if you do this with, you write down the Hamiltonian, it's really a Hamiltonian, it's a matrix that acts on an exponentially large Hilbert space. And what Steve White effectively did is bring down somehow this exponential complexity, something that is polynomial, that is actually linear in the size of the system. So because of somehow some good guesses of how this thing works. Actually, I think, so there's a very nice paper of one of the organizers here that with his collaborators, where they actually proved this. Okay, they actually proved that indeed ground states of gapped Hamiltonians, you can actually find them in polynomial time. So this is effectively like a computer science proof of the things that people had been using. But nevertheless, it's very nice that you can prove that there's no exceptions. And so how does this work in practice? How do you actually deal with these algorithms? Well, there's very nice linear algebra involved. Okay, so to find actually the ground states of these these many body systems, you kind of write down your NPS and you do a variational calculation of it. And the whole point is that actually when you have a Hamiltonian term like this and you want to calculate the expectation value, there's an efficient way of contracting that tensor network. So these are all matrices or tensors, and you have to contract them in a way such that the complexity of this does not grow exponentially. So if you would first contract all these indices like this, then multiply with h, and then multiply like this. This is what you would do if you do exact diagonalization. This is the normal way, the typical way people would do it. This would, of course, grow exponentially in the system. The amount of memory you need to store that wave function would grow exponentially in a number of things. But what Steve Weiss realized is that, of course, if you start contracting this with this, and then this with this, this with this, you never kind of grow to something that is larger than chi squared. So this is chi dimensional, chi dimensional. So you never get some object that is larger than a chi squared, that has chi squared degrees of freedom, and indeed somehow independent of the system size, you will be able to calculate expectation values. Okay, so effectively what this tells you is that indeed by looking at these states, there's some kind of a holographic principle there, that you map somehow the problem of a 1D system, like finding ground states of a 1D quantum system, to somehow the problem of evolving a zero-dimensional system in space or in time, and this is effectively somehow a holographic map. This is, of course, also how it will be done in higher dimensions. So what is interesting, and actually this is important for the second part of the talk, it turns out that it's not just the ground states that you can find. You can also find excitations. Okay? It turns out that excitations of above the ground state, because of course this is what physicists are really interested in, how do excitations above the ground state look like? Well, they live in some kind of, you can define a tangent plane. So you have a ground state somewhere, you define a tangent plane, you project the full physics on that tangent plane. This gives you an effective subspace. You kind of diagonalize the Hamiltonian on that subspace, and this gives you kind of ways of finding dispersion relation. Okay, how is the energy? Somehow you have a certain particle ansatz, so like how is the energy of the particles depending on their momentum? And this gives you basically, you can solve this using these ideas, using effectively machine precision. So what is interesting is that you can also, if you have symmetry breaking, actually, that these elementary excitations will be domain walls. Okay, so this is like if you have an Ising model in the symmetry broken phase, the elementary excitation would be like you have spin-ups, and then you have some domain wall and then spins down. These are the lowest lying excitations. You can also model these, and actually these domain wall excitations will be very important in the second part of my talk. Okay, so you can actually start doing this, like you can look at spinons, holons, all these different particles that people talk about, somehow they appear here. And these are really kind of objects that can be understood from somehow the geometry of this manifold. Okay, so you could also ask, okay, but okay, maybe as a field theory, I'm not interested in gap systems. I'm only interested in critical spin chains, or somehow what happens with systems with infinite correlation links. And indeed, somehow there is indeed a priori a problem, because if you have a critical system, so exactly a system that lies at the boundary between two gap phases, certainly there turns out to be much more entanglement. But the much more has to be kind of a little bit weakened down, because actually much more is just logarithmically more. And even somehow, so if you look at the block of L sides and you calculate the entanglement entropy of these sides, somehow of the reduced density matrix of these L sides versus the rest, the entanglement entropy still only grows logarithmically with the size of the block. If you would have a random wave function there, it would grow linearly. So there's still exponentially less entanglement, even for a critical system, than you would have in a random state. And indeed, somehow it turns out that from the point of view of the complexity, this is not a problem at all for matrix product states. People actually simulate, indeed, critical systems using this matrix product states. And what is interesting is that you get kind of a whole new area of time trying to understand finite entanglement scaling. So, of course, this bond dimension of these matrix product states, this number of variational parameters, is effectively introducing a finite temperature. It's like you sort of kind of simulating your system at zero temperature. Depending on the number of variational parameters, you kind of lower the temperature. Okay, so it's like you added a perturbation to the system that opens a gap, and then by varying somehow this number of parameters that you have, you do some entanglement scaling, and indeed you can kind of see that you have finite size scaling and entanglement scaling. All these things come out, and there's many kind of things. You have beautiful kind of collapses. Even if you kind of simulate these things in infinite systems, you can understand all of somehow these features of critical systems, at least somehow in this 1D, but people have also done this now in higher dimensions using somehow these finite scale entanglement ansatses. Okay, but let's go back to the main topic of this talk, namely phases of matter. Okay, so So the one thing that I have not talked about at all are the order parameters. Okay, then this was actually the whole point of Landau. Okay, Landau said, okay, this is an order parameter. An order parameter is what you need to determine a phase. Okay, so of course the most famous Hamiltonian is the Ising model in transverse magnetic field. I have like a ZZ term, I have an X term. Somehow, what is the symmetry of this Hamiltonian? It commutes. If I kind of apply the sigma x Pauli operator to all my spins, so these are spin 1/2, obviously then this commutes. So I have a Z2 symmetry. So that means that from the point of view of this group theory, I could have two phases, the symmetry broken and the symmetric phase. And indeed, you have the paramagnetic phase, which is the symmetric phase, the ferromagnetic, the Z2 broken, and there's a phase transition in between them. And the order parameter, the expectation value of somehow the magnetization, which should be 0 if somehow you have a symmetry, suddenly you get an expectation value of this. And this is the magnetization of your kind of thing. Okay, so this is order parameter, this is thing. And this was the situation for a very long time until an amazing paper actually, oh wait, there's a mismatch between what I see. Okay, between an amazing paper of Kadanoff and Seva in 71. Okay, so they were asking maybe there's also somehow something like an order parameter in the paramagnetic phase. Okay, so maybe there's an other observable that I can calculate that distinguishes that one that is non-zero in the paramagnetic phase and actually 0 in the ordered phase. Okay, so and they did an extremely careful study of the Ising. So this is for the 2D classical Ising, but it turns out that this is completely equivalent to what happens in the quantum case by doing some mapping. And what they realized that indeed, even in the ordered phase, there is actually an order parameter. There's something like a string order operator. If you kind of calculate somehow an expectation value of something like an x here and an x there, and you connect this with a string, so you calculate this expectation value, then in the ordered phase, this will be non-zero. In the disordered phase, this will be non-zero, and then 0 in the ordered phase, because it will kind of decay exponentially in the distance between these things. So what they realized is that there's some kind of a non-local order parameter. If you kind of look at non-local properties in the symmetric phase, suddenly you break the symmetry there. And how did they obtain this? By doing a duality transformation. And this, I think, certainly this, in the second part of the talk, this will be the key in trying to understand entanglement spectra. Somehow the features of all these topological phases of matter will be revealed by kind of looking more carefully at what duality transformations are. And indeed, this is how somehow they saw this. And actually, very quickly after that, there was followed up by a paper, a very famous paper of Franz Wegener, who also did this in higher dimensions. And actually, indeed, explicitly in the title already says that there is generalized Ising model and phase transitions without local order parameters. Okay, so this is these are actually gauge theories. This is the Z2 gauge theory, and this is a very famous paper, I think, that indeed started this whole idea that indeed the Landau paradigm is not enough. There are things that you cannot see by just looking at local order parameters. You also need to look at non-local order parameters, and indeed, this is what happened somehow in the Z2 gauge theory. There's, of course, this kind of the Wilson lines. There's non-trivial, non-local operators, non-local products, somehow products of many kind of operators that start, if the length of this line starts growing, somehow it does not kind of go to 0 in a phase, and it goes to 0 in another phase. So there's some kind of a way of distinguishing these different phases. It turns out to be related somehow. This is very much related to the toric code physics that Kitaev, of course, has been kind of making popular again, because it's very relevant for error correction. But anyway, so there's even in the 1D case. Let's go back to this Heisenberg spin chain. Actually, turns out that this is exactly how you can distinguish this SPT phase that I talked about from the rest. Okay, so actually Haldane in '83 already understood that the ground state of the spin Heisenberg model, okay, which was right in the middle of this phase diagram that I showed to this SPT, that it has some topological nature, and he kind of argued, he gave arguments of that, making use of somehow field theoretic arguments, but not too much later. Actually, there were two Dutch people, Deneys and Rommel, so they realized that indeed somehow the key the key that distinguishes somehow this topological phase from the non-topological one is that also there is something like a non-local order parameter. Okay, there's some kind of a string order parameter, namely if you calculate somehow the expectation value of that object when somehow n goes from n0 to n plus n0 and n goes to infinity, it does not go to 0 in exactly this kind of phase in which you have entanglement. So what is somehow the key, or how can we understand this? Of course, I think most of you, of course, know is that of course, somehow there's something special with the edge modes that happens in the system. But indeed, how can you see this from the point of view of this entanglement spectrum? So if you look at the entanglement spectrum in the half chain of this Heisenberg model that we showed in the beginning, you saw that you have also always two-fold, four-fold, two-fold, four-fold. You had all this degeneracy that were products of 2. Now, if you look at the symmetries of the spin-1 Heisenberg model, so what is the group somehow that governs the symmetry there is, of course, the group SO3. And there's, if you look at the representation theory of SO3, there's no E-reps of SO3 that have an even number of matrices. All the E-reps have an odd dimension, so 1-dimensional, 3-dimensional, 5-dimensional. Okay, these are, of course, the even spin representations of SU2. So it means that indeed somehow there is something, and the fact that this is always twofold, it means that there must be somehow hidden there that these entanglement degrees of freedom, they transform according to SU2 as opposed to SO3. So this indeed, and this is exactly what Haldane already kind of understood using his field theoretic arguments, that indeed if you would take such a spin-1 Heisenberg model, that at the edge you have dangling spin-1 half degrees of freedom, and if you kind of would do a global transformation on your somehow using a spin-1 transformation, that these edge modes, these edge spins would transform according to SU2, but not according to SO3. And SU2 turns out to be somehow a projective representation of SO3. It's a representation of SO3 up to somehow a sign. Okay, so and this turns out to be exactly somehow the symmetry that is responsible for the string order. Okay, so this will become much clearer in a few slides. But anyway, the essential paradigms here, and this is what is driving somehow this whole community and understanding, indeed trying to use entanglement to characterize phases of matter. Of course, in these simple examples, it's all very obvious, but of course, there's more examples where it's very non-obvious, is to kind of detect the global features of the system through somehow the fact that somehow the entanglement degrees of freedom, these local tensors, somehow transform according to non-trivial representation. So what you want to do is turn somehow the global symmetries of the system. You want to study how do these local tensors, okay, because I know that the ground state of the system is represented by this local tensor. How somehow do the global somehow features reflect themselves, or somehow the phase of my system reflect themselves, and somehow the symmetries of this local tensor. And this is indeed kind of going beyond lambda, because now this is not really about order parameters anymore. It's rather about how do my somehow local tensors that describe the ground state, how do they somehow encode this symmetry of my full system. Okay, so for this to make progress there, we need actually something that is called the fundamental theorem of matrix product states. Okay, so it tells you that if two matrix product states are equal, this is true if and only if somehow if I have a psi that with matrices AI, a psi with matrices BI, they are equal to each other if and only if there exists a gauge transform, somehow X that doesn't depend on I, such that somehow these two things are equal. So it's clear that indeed this arrow from here to there is obvious, because the wave function is the trace of the products of all these matrices. So if you conjugate all the matrices with the same X, then of course the trace of the product of these things does not change. Okay, but the other direction is non-trivial. Ignacio actually proved this using some beautiful Cauchy-Schwarz argument. What else? I think Ignacio is the master of Cauchy-Schwarz. So anyway, so this is basically the fundamental theorem that drives basically the full development of the theoretical insights of somehow everything that has happened in the context of matrix product states. Because we can immediately use this now in the context of global symmetry. So if I have a ground state or a wave function that is invariant under a global symmetry, okay, so this would be maybe the spin-1 height. This would be like SO3. This could be all the SO3s in somehow the previous example. I know that somehow my wave function, because I have a unique ground state, has to be invariant under that. Okay, so that means that this MPS, the global MPS, must be equal to this one. Now you use this theorem. It means that if I apply this UG to this, there must be another X, and in this particular case I know it VG, such that this is equal to this. But now you see a very big difference. This UG comes alone, but this VG comes in pairs. Okay, so let's actually check this, let's say, for the AKLT model, and maybe just take 4 elements of my SO3. Just let's look at diagonal somehow transformations of SO3, a subgroup Z2 times Z2 of SO3, and let's see how these symmetries on the physical level are reflected on the virtual level. So all these matrices commute, but on the virtual level, it turns out for the AKLT system that all these matrices that correspond to this are just the Pauli matrices. And the Pauli matrices obviously don't commute. These matrices commute, and indeed, you can easily see that actually these Pauli matrices, they form a projective representation of Z2 by Z2. Okay, so it means that actually, even if your system transforms, kind of you have a global symmetry, that the entanglement degrees of freedom can transform according to some projective representation of that symmetry. And it turns out that this turned out to be the whole classification. This is exactly the key in understanding the entanglement, but also somehow the phase corresponding to this AKLT phase. The fact that indeed in that phase, all these tensors will transform projectively. Okay, so the immediate consequence of this is that indeed you have these degeneracies in the entanglement spectrum, because if you have a projective representation, this cannot be somehow abelian. You cannot have somehow, you cannot have you cannot reduce somehow a projective representation to 1-by-1 blocks. Okay, so whenever you have something that transforms according to a projective representation, you must somehow, the E-reps corresponding to this must be higher than one-dimensional, and therefore somehow you will automatically have degeneracies in this entanglement spectrum. So this is somehow the thing we want to understand indeed. So we have these entanglement spectra, and these entanglement spectra somehow convey the information of what is the phase that you're living in. Actually, I don't really have time, but you can do the same thing for systems with fermions, but let me kind of skip this. But anyway, so this is this generalized Landau paradigm for 1D systems. Okay, so that the first ones to understand this in complete generality, I think, was Xi Chen, Xiaogang Gu, and Xiaogang Wen, almost 13 years ago now, I think. So they basically understood that indeed, if you have quantum spin chains and you want to kind of understand the phase diagram of this, it's not enough anymore to look at subgroups, but you also have to look at all possible somehow projective representations of these subgroups. Okay, so you have a big group, you look at all subgroups, you look at all possible projective representations of these subgroups. Actually, if you have time reversal and reflection, you have to kind of modify a bit. That's why there's even some kind of non-trivial action there. But this is effectively the whole story. Okay, so this is the way you can characterize phases of matter with respect to certain symmetries. Okay, so let's, but this turns out to be not the complete story yet in 1D. Okay, so in 1D we think, okay, this is it, no? Because I have now kind of understood what happens when I kind of have how to characterize quantum spin systems with global symmetries. It turns out that there's also many quantum spin chains that actually can be defined without the tensor product structure. No? But for example, kind of theories that arise from gauge theories, or so-called anionic spin chains, or quantum spin systems that have some non-trivial 3 co-cycle symmetries. So there's many kind of analogs of also these things, of course, in field theory. But there are clearly lots of interesting spin chains for which there is not an obvious tensor product structure, and these are typically realized on the boundary of a topological theory in higher dimensions. Okay, so these are effectively describing the edge modes of a topological theory. But what is one of the most surprising things, at least to me in recent years, it turns out that actually these generalized symmetries also appear in normal quantum spin chains. It will turn out that if you want to somehow, this is where I want to go to now in the next slides, is that if you want to understand completely somehow the physics of normal quantum spin chains, that you also have to include these generalized symmetries, because some dual models of the original model will have generalized symmetries. Okay, so that is not enough to understand the physics of something, to understand just this one. You also want to understand all dual theories. And so the examples of states that have this are these famous IRF, interaction around the phase Hamiltonians, I think originally introduced by Baxter. There's also these anionic spin chains introduced, I think, 15 years ago by Feigwin, Kitaev, many people. They called it the golden chain. These are kind of spin chains that are defined on constrained Hilbert spaces. Somehow, if this is a 1 and a tau, then actually this spin cannot be anything. It has to kind of, you have to be obtained, but it have to be obtainable by multiplying tau by tau. So if this is a tau, this can be a 1 or a tau, but if this is a 1 and this is a tau, then this must be a tau. So not all somehow, there's a constrained Hilbert space. So for a computer scientist, it just can have some kind of Fibonacci sequence that defines my Hilbert space. The Hilbert space is all kind of sequences that are satisfy Fibonacci. Namely, if I have a 0, it has to be followed by a 1, but if it's a 1, it can be followed by a 0 or a 1. Okay, and this is effectively how you define your Hilbert space, and it turns out that this is a very natural Hilbert space if you kind of look at the edge of higher dimensional theories. Okay, but I will kind of come to this. So now, what is interesting is that the symmetries in these spin chains and these kind of more general spin chains, they are not necessarily described by a group anymore, but rather by some kind of a fusion category. So there's a whole, I think this has been an extremely active field of research in the last 30, 40 years in mathematics, is indeed to generalize this whole idea of groups to something that is called fusion categories. And indeed, somehow means that if I have an element and another element, somehow the product of these two is not just one new one like in a group, but I can have a sum of many kind of elements. So for example, these are the rules for Fibonacci. You also have different rules for this interaction around the phase, which is effectively the fusion rules of the E-reps of SU2. Okay, so What is interesting is that the representation theory of these fusion categories has been completely worked out. So these are, at least for me as a physicist, extremely kind of difficult papers. Okay, it turns out that invertible bimodule categories are what somehow are the equivalent of the representation theory of groups. Okay, so what you have to look at, if you want to find all representations of such fusion categories, you kind of need to come up with something that's called invertible bimodal categories. And I think since then, somehow, since people realized that this is interesting in physics, I think they, Pavel Ittinghoff and his collaborators sold many more books. Anyway, so what is interesting and what I understand very well is that actually turns out that all these bimodal categories, these invertible bimodal categories, have very simple representations in terms of matrix product operators. Okay, so if you have a normal kind of group symmetry, like a global group, then this was just a tensor product. I acted with somehow with symmetry gamma here, gamma there. So I acted with the tensor product of all my same symmetries. Now, what these more generalized symmetries do is that the action that I do on this one spin is correlated with the next action, and this action is correlated by some virtual index. Okay, so by a matrix product operator. So this is very similar to a matrix product state, but it's an operator now. And it turns out that if you require that these matrix product operators form a representation of this fusion algebra independent of the system size, then you can derive a whole wealth of kind of relations between them. Okay, so you can start deriving all possible properties. And actually, the key property that you need to use is this fundamental theorem of matrix product states, but you have to apply it now in the context of matrix product operators. So if this times this must be n alpha beta gamma with n independent of the system size times this gamma, so a representation of that fusion algebra, then somehow these MPOs, these elements, these tensors, will have lots of symmetries. And indeed, somehow, turns out that for a bimodule, you can find exact kind of representation. So a bimodule is something like I have different categories. I have a category C, I have a different category D. I also have a module. So this module, elements of this module are only defined if you kind of multiply from the left with elements of your category C or kind of simple objects, from the right with simple objects of D. So there's kind of whole type of rules of how the constraints work. What are the constraints? If this is like what if M and D, they can fuse to this. These are all kind of fusion rules. And you can start kind of building up the same mathematics like people do in normal groups. Okay, so normally if you kind of have a certain representation and another one, so I have a certain EREP and another one, then of course the tensor product of these two I can reduce by defining Clebsch-Gordons. Okay, so this is exactly somehow one of these things. So if these would be just tensor products, this is a tensor product of this is U of G, tensor U of G, and there's a Clebsch-Gordon coefficient that maps it somehow to the fusion rules of these different representations. Okay, this is a spin 1/2, a spin 1/2, this would be a spin 0 or a spin 1. Okay, but you can start doing now exactly the analog of somehow all these, somehow display the same game. So you can define Clebsch-Gordon coefficients for these matrix product operators, both in this direction, in this direction. This leads to some, to apologize that these slides are pretty dense, but anyway, you can just do the systematic kind of generalization of group theory in terms of these matrix product operators. And using this fundamental theorem, you kind of end up with skeletal data of somehow this whole module for this category. And again, I don't want to go too much in detail because I really want to convey mainly why all of this is relevant. Because actually you would think, oh, I don't need this to understand this. It will turn out that this will have very tangible kind of uses in normal tensor network algorithms. Okay, so anyway, so the reason for this is that indeed, if you have a system with such kind of symmetries, you can also define a generalized Wigner-Eckert theorem. Okay, so Wigner-Eckert theorem, I think, yeah, I don't know who Eckert was, but Wigner was also here in Princeton when he formulated this. Is effectively that once you have like an object that commutes with all your symmetries, then it must be able to write it down in terms of Clebsch-Gordon coefficients. Okay, that's a very kind of simplistic way of rephrasing the Wigner-Eckert theorem. If I have an object that is symmetric, you must be able to write it down in terms of its Clebsch-Gordon coefficient. And it turns out that exactly the same thing happens here for these MPOs. And what happens then is, because somehow these Clebsch-Gordon coefficients, they have to satisfy lots of kind of non-trivial constraints, you will be able to kind of come up with many different realizations of somehow the same theory. Okay, so it will turn out that for the same, you will be able to find that for a given fusion algebra, there's many different realizations of somehow the same objects. So I don't know how much time actually I have left. We started like 15 minutes late. But I can stop if I have to stop in 10 minutes? Yeah. Or 15 minutes? Yeah, okay. But anyway, so what is, what is very interesting is that, well, we developing this, and actually this was mainly, of course, my my students that were doing this in terms of these explicit representations. So what I wanted to, maybe I didn't stress this, but what is very interesting is that these matrix product operators give really somehow the explicit matrix representations of these fusion categories. They give just matrices that you can even put in the computer, just like normal representation you can put in the computer. These somehow all these bimodules are realized by these MPOs, and you can also find all possible dual ones. Okay, and this is actually starts being very interesting, because if you kind of find all possible different realizations of these same fusion algebras, you can also start defining intertwiners. Okay, so, and again, bear with me, because probably you will say, oh, I don't need to know all of this, but it will be very interesting because it will kind of allow you to understand much better somehow the structures of entangled phases of matter. It tells you that actually if I have dual theories, because remember, this was also how Wegner, but also Kadanoff and Seva derived their non-local operators. Okay, they realized that there were non-local order operators in somehow the symmetric phase by doing duality transformations. Okay, so what we're saying here is that actually this matrix product operators, or this kind of generalized symmetries, they are dual symmetries, maybe even two normal symmetries. And I want to understand all possible dual theories that parameterize a certain kind of theory. And for this, you can construct matrix product operator intertwiners that will map a certain Hamiltonian to another dual Hamiltonian. Okay, so you have a certain Hamiltonian, and this matrix product operator intertwiner has kind of different kind of modules, one here and another module him. And somehow this intertwiner will allow you to map somehow all possible theories to all possible dual theories, and this is solely dependent on the symmetries of your system. Okay, so again, this is something that these dualities, this turns out to kind of give you a complete, explicit way of understanding all dualities that people have constructed in the literature. Like, and this has a very explicit kind of representation in terms of these matrix product operators. And it turned out that actually, if you do this using these tensor networks, you can see that all these duality transformations are actually unitary transformations if you include somehow the boundary conditions as quantum degrees of freedom. Okay, so this is something that probably all of you, or many of you, or certainly the condensed matter physicists of you know very well, that if you do something like a Jordan-Wigner transformation, you have to be very careful with the boundary conditions. The boundary conditions and the charge sectors start interchanging and all this. So that means that indeed you feel that, okay, these duality transformations are not unitary because they are kind of changing things. But if you kind of just lift these boundaries to boundary degrees of freedom, and you can do this with something that's called tube algebras, then actually all these duality transformations can be proven to be unitaries. Okay, so they completely preserve the spectrum. Okay, so let's in the last 5 minutes, let's kind of try to see how this explains effectively all these phases of matter in the 1D case, and of course then I want to go to the higher D case, but there will be no real time. So let's go back to this whole phase diagram here. So I have this phase diagram of this spin 1 Heisenberg model. This was the SPT phase, symmetry broken phases, all these kind of things. What I have kind of seen is that there's a complete generic way for a given symmetry to find all possible dual theories. And it turns out that for every kind of symmetry in this phase diagram, there's also exactly the same label that can be used for defining a duality transformation. Okay, so the way that all these duality transformations worked that I just talked about, somehow the way you can classify all duality transformations, and this is actually something that is constructive, is exactly by using all the possible labels in which you can break the symmetry. Okay, so this is, of course, not a coincidence. So it means that actually what is the interesting question is now, if I'm in a certain phase, so I have this whole phase diagram, for example, in the SPT phase, what are all the possible dual theories? Are there dual theories where there's much less entanglement in this kind of thing? So again, all these DMRG methods, all these tensor network methods, the less entanglement there is in the system, the better they work. Okay, so this entanglement is the key in understanding the things, but also from the very practical point of view, you want to simulate a quantum spin system, you want to simulate something that people have in the lab, you want to use the representation with the least amount of entanglement. Turns out that for every one of somehow these phases, there's a unique dual theory where all symmetries are broken in this dual theory. And this is something that I found really kind of I found this very exciting. So it means that actually in this SPT phase, it doesn't matter what phase diagram you have. Okay, for example, you're in this phase, the symmetric phase, there is actually a dual theory where all symmetries, all dual symmetries are broken, and there's much less entanglement. Okay, so if you're in a symmetric phase, you will have very large degeneracies of your entanglement spectrum. Okay, so your entanglement spectra, somehow they will have large degeneracies. This will cost you lots of kind of computational power to deal with. But there is always a dual theory where all the Schmidt numbers are basically distinct. Okay, so also this SPT phase, we saw, okay, this SPT phase is one, this topological phase is one with lots of entanglement. But what you can actually show now is that what you can prove is that there's actually a dual theory where all these Schmidt coefficients are broken, where you're in a completely symmetry broken phase. And this is exactly this paper. Actually, I really wanted to have this paper before I gave this talk. That was written by Lawrence Lotus, Clément Delcourt. So they were really kind of the ones who did the real work. I kind of just did the coding to actually kind of try to understand how this works. So there's a very beautiful categorical kind of reasoning behind this whole kind of idea of dualities and symmetries. It turns out that if you have a category C that encodes the symmetries of your system, this could just be a group. Okay, you have a certain way of representing them, and these are the EREPs of this kind of representation. So for a normal group, this would be, let's say, this VEC-G, this would be VEC, and this would be REP-G. So this would be the EREPs. The EREPs form a fusion category. So for a given phase, you want to choose your MPS in such a way, or your dual theory in such a way, that somehow all your symmetries are broken. And this gives you somehow a complete way of building up all these different matrix product states and all these different phases. And it turns out that all the degeneracies of the Schmidt spectrum are coming from multiplying the ideal, the kind of computationally least expensive matrix product state by these matrix product operator intertwiners, and these introduce all these degeneracies in the entanglement spectrum. So you can actually kind of make this hard, and you can actually see this, like for a given, you're in the SPT phase, you can write down, okay, what are all the possible dual theories. We developed some kind of a new DMRG code that can deal with all these different kind of cases. It's a completely constructive way, and you can look at the entanglement spectra, and immediately in the I4 symmetric phase, you see indeed somehow if I look at somehow the rep size, so this is basically the projective representation of A4, the Schmidt coefficients are decaying much faster than somehow any other kind of things. And you can indeed also see how much memory do I need. So this, you can use this to kind of turn all somehow to this DMRG calculations into much more practical tools. So you can do the same thing for the symmetric phase, for other symmetric phases, and actually this is something that is completely generic. And I think this is very exciting because it allows you to see that indeed somehow all these entanglement spectra and actually phases of matter are, of course, completely determined by somehow these entanglement degrees of freedom, and somehow the fact that there are different ways in which this entanglement can be introduced. And it turns out that the category that you kind of need to kind of have all this symmetry breaking is completely governed by the excitations in this theory. So remember in this beginning of the talk, I talked about these possible domain wall excitations. Okay, so this domain wall excitation, it turns out that it's in the perfect dual theory where that breaks all the symmetries, all the excitations are of the domain wall kind. And so the symmetry is completely broken. That means that if you act with the symmetry on any of the ground states, you get always another state. Okay, this is obviously less entanglement. This is extremely interesting, both from the conceptual, but also from the practical point of view. So I think I will have to stop here, but let me just kind of say that indeed all of this has to do with this idea of generalized Landau paradigm. How can you understand phase of matter? How do you think of symmetries in many body wave functions? And indeed, there are extremely interesting ways in which these symmetries manifest themselves, even in these simple 1D cases. It turns out that somehow there's a whole machinery that you can use in terms of category theory to come up with a better understanding. And even if your kind of original system has normal on-site symmetries, it turns out that it might be much better to look at another dual model that has exactly the same spectrum with categorical symmetries. Of course, so we can repeat this now in higher dimensions. It turns out I will not continue, so I will stop here. But so all of this can now kind of course be lifted to higher dimensions. And this is exactly the whole idea of PEPs. Like all these 1D systems with these categorical symmetries, they can be understood as boundaries of 2D theories. You can construct those. You can start looking actually at these higher dimensional systems. They are actually realizing something that Feynman was dreaming about. So Feynman was dreaming about if you kind of have a many body system and you want to kind of look at a certain region of the system, so you look at a certain subsystem A, he said it doesn't make sense to have to kind of keep track of all the degrees of freedom of my system. I only want to keep track of the things that happen on the boundary because that's where everything kind of is happening. But he didn't really have an explicit way of doing this. And it turns out that this is exactly what these tensor networks do. They effectively parameterize somehow the degrees of freedom that live somehow that separate the system from the rest. You give a tensor product structure to these degrees of freedom, and you can start studying basically how these symmetries look like. And indeed, somehow all these, so there's a whole wealth of extremely interesting results that have been obtained in the field of condensed matter physics, also in the field of quantum error correction. Actually, really kind of mostly inspired by the work of Alexei Kitaev and Xiaogang Wen, all these string nets and all these kind of things. Turns out that all these things have very natural tensor network descriptions. And all these states also, because of exactly the same reasons as I kind of sketched in the 1D case, they satisfy area laws, because like a string net is by construction effectively somehow a PEP. So anything that is the ground state of set of commuting terms is trivially can trivially be written down in the form of these tensor networks. That means that every state in that phase is also kind of, you can effectively parameterize using these string nets. And you can start looking now at the symmetries. What are the symmetries that appear in these higher dimensional systems? And again, you get somehow these different kind of Wilson type of strings that they are form, instead of normal group-like symmetries, they are kind of fusion-like. And you can start looking at things like this entanglement entropy from this tensor network point of view. And indeed, somehow, because these tensor networks give an explicit representation for the entanglement degrees of freedom, you can see that indeed, if I have symmetries, if I have some non-trivial symmetries, there's somehow, there's degrees of freedom missing, okay? Because not every state on these virtual indices can be realized. There's some symmetries, and this is exactly somehow this deficit is exactly this topological entanglement entropy. You can look at order, you can look at, actually, there's a whole, in the hierarchy community, there's an extreme active program going on that is called SymTFTs or duality defects, and all these kind of things seem to, but I'm not an expert in this, but it seems that this is very much related somehow to this whole discussion that we're having here. If you start from a topological theory, like a wave function of a string net, and you start taking maybe some overlap of this string net with a product state, this gives you a partition function of classical stop-mech model that still has all somehow the same symmetries. All these tensors still have the same symmetries, and this seems to be very much in line with work that people in the high energy community have been doing, and I would be very interested in certainly kind of doing this. And you can start looking at dualities in higher dimensions. You can start looking at what does it mean to gauge. You can start looking at higher dimensional Jordan-Wigner transformations. But let me actually just kind of go to conclusions. Of course, there's also very interesting connections with error correction, but anyway, so let me just conclude that entanglement theory is probably a key ingredient for characterizing phases of matter, especially the ones that exhibit topological order. And indeed, somehow the generalized Landau paradigm, and I think the first person to really appreciate this was Xiaogang Wen, is that indeed the global symmetries of a system, if you have a tensor network, can be kind of looked at by just looking at the local symmetries, the local tensors. What are the symmetries of the local tensor? This is the new kind of order parameter. How do your local tensors transform? And what I particularly like in this whole program is that these tensor network kind of ideas, they give very tangible and practical applications by using actually pretty deep mathematical ideas. This is something like you really have to make use of these bimodules to come up with the state-of-the-art simulation methods for normal quantum spin chains that people have to deal with every day. And there's actually a very large community of computational physicists that is using these tensor networks. But anyway, so there's still many open problems, and yes, I want to thank actually the audience for their attention. And before finishing, I had to nominate 3 people, I think, for the discussions. And so this will be Ignacio for the, I don't know what group you are, the red group, Lorenz Lotens for the green group, and the blue, and then Norbert Schuch for the remaining one. Okay, thank you.
Okay, we'll take a few questions now, and then we can ask more questions in the discussion.
So you mentioned the Fibonacci fusion rule on spin chains. Did you have in mind a tensor product in the space of spin chains or the amniotic chain?
So of course there's no tensor product structure anymore, no, because you don't what you do here is depending on what happens before, but there's a realization. So it's a subspace of something with a tensor product structure, of course. Okay, so it's clearly a subspace of a qubit. Like if you take n qubits, it's a subspace. It's namely the subspace spanned by all sequences that satisfy the Fibonacci rule. And in that sense, it doesn't have a tensor product structure anymore. And indeed, if you look at the symmetries of these things, the symmetries of these things are not realized using normal kind of tensor products, but actually using these categorical symmetries.
The Fibonacci rule realized only in the subspace or also on the bigger space?
Well, it's realized on the bigger space because your theory is only defined on the subspace in the bigger space. But you can write down, at the end, you find, if you do representation theory, you have to do representations in some space. You have to write down this thing in some space, and the space is, in this particular case, this matrix product operator is indeed, has a tensor product structure, but you have to, of course, only look at the subspace that is relevant.
So you defined, I think, adiabatic, like going from one state to another adiabatically as low depth. What do you mean by that? Like polynomial depth, or? I think most of that. It should not be.
So this is exactly what Matthew Hastings proved in his quasi-adiabatic theorem, is that if you have two Hamiltonians in the same phase, then there will be actually a Hamiltonian evolution with a dressed Hamiltonian. You have to dress the Hamiltonian with some kind of tails, such that if you follow this unity evolution, you will exactly go from one ground state to another one. And actually, the time in which you have to evolve is not really depending even on the system size.
Range of entangled states can be prepared in adiabatically from the product.
Yes.
So, like, to me, that doesn't make any sense. Like many states can't, many ground states of Hamiltonians can't be prepared in constant depth.
Okay, but you have to be careful. This is a Hamiltonian with exponential tails. Okay, so it's not strictly Hamiltonian evolution. Okay, that means all the correlations that build up, they are really exponentially suppressed. So this is this program of Hastings. You take a Hamiltonian, you kind of modify the Hamiltonian by dressing it with some tails, exponential tails, and then if you evolve with that new one, this is exactly giving you somehow the evolution and that manifold. And that's the reason that actually everything has an area law, and actually that you can define even somehow these phases in this way in terms of quantum circuits. But we can talk later about this.
Okay, thank you. We'll postpone the rest of the questions in the discussion session.